What specific problem does your proposed method aim to address in the context of mathematical reasoning tasks, and why is identifying critical tokens significant?
The proposed method aims to address the problem of incorrect reasoning trajectories in mathematical reasoning tasks by identifying critical tokens that lead to erroneous outcomes. These critical tokens disrupt logical flow, misrepresent relationships, or introduce computational errors, significantly impacting the final result. Identifying these tokens is crucial because avoiding or correcting them can often lead to correct outcomes, even when the overall reasoning context remains unchanged. The method employs a novel contrastive estimation strategy to automatically detect these critical tokens, which is essential given the high costs and scalability challenges of existing methods. By effectively identifying and penalizing these tokens, the proposed approach enhances the accuracy of reasoning models, as demonstrated by improved performance metrics in experiments.
Can you provide a detailed breakdown of how the proposed contrastive estimation strategy works step by step, including the training of positive and negative models?
The proposed contrastive estimation strategy involves several key steps to effectively identify critical tokens in reasoning trajectories. First, two models are trained separately: a positive model on correct reasoning trajectories and a negative model on incorrect ones. This is achieved by sampling a dataset where reasoning trajectories are generated using a pre-trained language model, with correct trajectories labeled as positive and the top P% of incorrect ones as negative. Next, for each token within an incorrect trajectory, the strategy calculates a contrastive likelihood score, where a low score indicates a high likelihood of being a critical token associated with incorrect outcomes. The scores are computed using the likelihoods from both models, allowing the identification of tokens that significantly disrupt logical reasoning. Finally, these identified critical tokens can be replaced or avoided in the reasoning process, leading to improved accuracy in the model's outputs, as demonstrated by the significant performance gains observed in the experiments.
Illustrate the inner workings of the critical token identification process with a simple example, explaining the significance of this example in the broader context of your approach.
In our approach, the identification of critical tokens is exemplified through the token ode, which misleads the logical deduction process in reasoning tasks. For instance, in an incorrect reasoning trajectory, if the token ode is present, it consistently leads to incorrect outcomes, as demonstrated by our token score calculation method. By resampling this token while keeping it unchanged, we found that it received a score of 0, indicating its critical role in driving the trajectory toward an incorrect conclusion. Conversely, when we replaced ode with an alternative token like paid, the accuracy of the reasoning significantly improved, showcasing the effectiveness of our forced decoding strategy. This example underscores the broader significance of our method, as it highlights how identifying and avoiding critical tokens can dramatically enhance the performance of reasoning models, ultimately leading to more accurate outcomes in mathematical reasoning tasks.
What are the specific advantages that your method offers over existing approaches such as resampling and Monte Carlo tree search, particularly in terms of scalability and efficiency?
Our proposed method, contrastive estimation, offers significant advantages over existing approaches like resampling and Monte Carlo tree search, MCTS, in terms of scalability and efficiency. Unlike resampling and MCTS, which incur prohibitively high sampling costs and face scalability challenges, contrastive estimation effectively identifies critical tokens by leveraging models trained on both correct and incorrect reasoning trajectories without the need for extensive sampling. This method allows for automatic detection of critical tokens, circumventing the limitations posed by the absence of human-annotated token-level datasets that hinder the training of dedicated detection models. Additionally, contrastive estimation utilizes token-level likelihood comparisons, which streamline the identification process and enhance the model's ability to learn from critical errors efficiently. Overall, our approach not only reduces computational overhead, but also improves the accuracy of reasoning outcomes by focusing on the most influential tokens.
How did you validate the effectiveness of your method, including details on the experimental setup, datasets used, and specific metrics employed to measure success?
To validate the effectiveness of our method, we conducted experiments using the GSM-8K and math datasets, focusing on 100 incorrect reasoning paths sampled from the GSM-8K dataset. We employed a contrastive estimation approach to identify critical tokens, where we compared the performance of models with and without these tokens by sampling 64 completions in each scenario. The accuracy of the models was measured using the PASIT-K metric, with significant improvements observed when critical tokens were replaced, such as an increase from 99% to 11% accuracy in the DeepSeek Math 7B model. Additionally, we implemented our proposed cDPO method, which achieved accuracies of 65, 69%, 69.09%, and 53% across different models, demonstrating its superior performance compared to traditional methods. The results were statistically validated, confirming the competitive advantage of our approach in enhancing reasoning accuracy.
Discuss the limitations of your method. Are there scenarios or conditions under which the approach might underperform, and how could future work potentially address these challenges?
One limitation of our method, particularly the contrastive estimation approach, is its reliance on the availability of a diverse set of incorrect reasoning trajectories to effectively identify critical tokens. If the sampling of incorrect trajectories is not representative or lacks variety, the model may fail to capture all critical error patterns, leading to suboptimal performance. Additionally, the method's performance could be hindered in scenarios where the critical tokens are not distinctly different from non-critical ones, making it challenging to differentiate between them based solely on token-level likelihoods. Future work could address these challenges by enhancing the sampling strategy to include a broader range of incorrect trajectories, or by integrating additional contextual information that could help in distinguishing critical tokens more effectively. Furthermore, developing a more robust model that can adaptively learn from evolving reasoning patterns could improve the method's resilience to varying conditions.